In this video, we'll get an introduction to the integration by substitution technique. First, we're going to start by remembering what the chain rule does in differential calculus to help us take the derivative of a composition of two functions. After that, we'll introduce ourselves to the integration by substitution technique, which is just a way of reversing the chain rule for derivatives. At the end, we'll get a look at a couple of tips and hints in using this substitution method effectively. So what's the chain rule? Remember, the chain rule is a rule from derivative calculus. It tells us how to take the derivative of a composition of two functions. Remember, a composition of two functions is when we feed the output of one into the input of another. In a notation, that would be something like f of g of x. And the chain rule says that the derivative of f of g of x is the derivative of f evaluated at g of x, so you take the derivative of the outer function evaluated at the inner function. But then you multiply that quantity by the derivative of the inner function. So for example, if I have the quantity x to the fourth plus x raised to the third power, then the outer function is the cube in this example. The inner function is x to the fourth plus x. So its derivative, we'll take the derivative of the outer piece, so the cube becomes 3 times blank squared. And then we evaluate that at the inner function, x to the fourth plus x, so that gets left alone. Then we multiply by the derivative of what's on the inside. So we multiply in this case by 4x to the third plus 1. You might want to do a few examples of the chain rule for derivatives before you start this section on integration by substitution, just to remind yourself of how it works. So the goal of integration by substitution is to take the chain rule and run it in reverse. In other words, we would like a way of finding the antiderivative of a composition of two functions when that composition is set up so that we can reverse the chain rule. In other words, how could we know, beginning from the derivative we had in the last example, 3 times x to the fourth plus x squared times 4x cubed plus 1, how could we know how to go backwards to the original function of which it was the derivative? Well, first let's make several observations. First of all, there is a composition of two functions happening here. The inner function, x to the fourth plus x, is being fed into the outer function, 3 times the quantity squared. So there is a composition going on here. Second observation is that there's a multiplication, that the composition is being multiplied by its own derivative on the outside, 4x to the third plus 1. Now, in general, if we're trying to take the integral of the product of two things, whenever there's multiplication and we're trying to take an antiderivative, we could be stuck. But the fact that the derivative of that very inner function, x to the fourth plus x, is a factor on the outside, 4x to the third plus 1, is what makes this method possible. Then according to the chain rule, what we're looking at here is f prime of g of x times g prime of x. And the chain rule tells us that the antiderivative is then just f of g of x. So this is how it would look if we were doing it just by reversing the chain rule. But our goal here is to make this process more systematic. In other words, we want to come up with a way that works, that avoids some of the having to be ingenious in how we observe that the chain rule works backwards. So what we're going to see is a method called integration by substitution, which is exactly the chain rule run backwards, but to make our lives a little easier, we use a little bit different notation for how to do it. So let's take a look. A lot of times when people think about substitution that have taken a course like Calculus 2 before, they think of it as a process called so-called U-substitution, a lowercase u being used here. And the role of the lowercase u that we're going to use in our substitution is it's going to denote our inner function, the function that's on the inside. We used to call it g of x when we were doing the chain rule, but we're going to call it u in this example. Historical reasons, I'm sure. So let's revisit this example again. 3 times x to the fourth plus x quantity squared times 4x to the third plus 1. If I want to take the antiderivative of that with respect to x, then the way the method of substitution works is I want to take my x's and trade them out for a different variable, which we're going to call u. And when we do that, the integral supposedly should get simpler in form, and therefore we should be able to do it. But when I trade x's for u's, I also have to trade the differential element dx for the differential element du. So let's see how that process works. Again, u is the inner function here. And our integral is set up in such a way that the derivative of that inner function, that x to the fourth plus x, happens to be a factor multiplied on the outside. That's an important part of the setup here. So because this integrand is set up in that fashion, we should go for it. We should try this method of substitution by setting u equal to x to the fourth plus x, so that my first factor here in this integral can be replaced by u. Then, to figure out what dx should be replaced by, Let's use Leibniz notation to denote the derivative of u. So du divided by dx. Remember, it denotes the derivative of u with respect to x. And in this example, du over dx is 4x cubed plus 1. And here's where we get to do a little sleight of hand. Take the Leibniz notation and treat the du and the dx as different parts of a fraction, so that we can isolate the du and the dx by themselves. And for example, solve for du, which is going to be in this case 4x to the third plus 1 times dx. What that allows me to do is look back up into my integral and say, oh, I have a 4x to the third plus 1 dx. So I'm just going to call that du. And now I have an integral where all of the x's have been switched out for u's, and I can now take this integral with respect to the new variable u. So now we can finish. Antiderivative of 3u squared as a function of u is just u to the third power plus c. We're not done, of course, until we get rid of our u's and go back to x's, because any problem in which we're asking a question about a function of x, we should answer using a function of x as well. So just remembering that u is equal to x to the fourth plus x, we get our antiderivative, x to the fourth plus x, the quantity to the third, plus c. Again, we knew that just thinking about the chain rule explicitly, but now we have a process, a method by which we can apply this backwards chain rule just by identifying a u and trading out x's for u's, and then trading out dx's for du's using the derivative of our inner function that we're substituting. Let's see how this works in a second example. This time we'll do a definite integral, the integral from 1 to the square root of e of the function x over x squared plus 1 with respect to x. So how does it work? First thing we want to do is find our inner u. In other words, find that inside function whose derivative is also a factor on the outside, an outer factor. So in this example, we might look at this integral and think, well, x squared in the denominator there, its derivative looks an awful lot like the x that's multiplied on the top side of this fraction. So we might be tempted just to go ahead and substitute u equals x squared. Then du would equal 2x times dx. And to finish substituting dx's for du's, one simple method for that is just to solve that equation for dx, and then substitute. So dx is du divided by 2x, which allows me to make that substitution and cancel the x on the top from the x on the bottom. And when all that dust settles, I end up with the integral with limits of x equals 1 to square root of e. I like to put that x equals down there just so that I don't forget that these limits of integration were limits on x and not limits on u. But then my integrand is du over 2 times the quantity u plus 1, which is better than our original integrand, but it's still kind of messy. So here's a tip. Why don't we just include that plus 1 from the original integral in the denominator in our u? If I do that, it turns out that du is still equal to 2x dx, so dx is still the same as it was before. And substituting x squared plus 1, all of that for u, now I get a much simpler integral, du over 2u. And that I can do. Pulling the 1/2 out in front of the integral, I get the integral of 1 over u with respect to u. Antiderivative of 1 over u is natural log of the absolute value of u. And again, I've retained the limits of integration here as limits on x. So before I substitute those into this expression to finish my definite integral, I have to trade u's back for x's, remembering that u is equal to x squared plus 1. Then substituting the square root of e and 1 in for x and subtracting, I get my result, 1/2 times the quantity, natural log of e plus 1, minus the natural log of 2. Here are a couple of tips on using integration by substitution to finish out this video. First of all, not every integral for which integration by substitution is useful might look like it in the beginning. So watch for secret inner functions. In this example, the antiderivative of x times the square root of x plus 1 has a natural inner function, u equals x plus 1. From which du is equal to 1 times dx. And when we make that substitution, we actually end up making quite a bit of progress here. The problem, though, is I can substitute x plus 1 for u and dx for du, but that doesn't do anything to fix the fact that I have this pesky x out in front of my square root. So to be able to trade out that x for u, I'm going to go back to my relationship between u and x that says u is equal to x plus 1. Well, if u is equal to x plus 1, that means that x is equal to u minus 1, so solving that equation for x will show me how to finish substituting my x's for u's. So now I get the integral of u plus 1 times the square root of u with respect to u, and this is a little bit nicer because now we can distribute the square root of u across the subtraction u minus 1. and get two separate terms, each of which is a power of u to the 3/2 minus u to the 1/2. And now we can take that integral with respect to u to get 2/5 times u to the 5/2 minus 2/3 times u to the 3/2 plus c. And then substituting x plus 1 back in for u finishes this integral. So even when it doesn't look like the derivative of the inside is on the outside, you might want to try a substitution anyway, just to see if something like this might happen after all. And finally, integration by substitution does not always apply to a given problem. In other words, this isn't the magical key that unlocks every antiderivative of one thing times another thing, or one composition of two functions for that matter. So here, the integral of the exponential of x squared, you might think, would succumb to a substitution for u equals x squared, du equals 2x dx, and so I can substitute dx equal to du over 2x, yet again. The problem, though, is that that introduces an x in a place where we can't get rid of it. We're stuck with that 2x in the denominator here, whether we like it or not. So it turns out that this integral, e to the x squared dx, does not yield to the method of substitution. In fact, even more is true. This is an example of a function which does not have an analytic antiderivative. So substitution only works if the setup is exactly right, if the derivative of that inner function is a factor on the outside. In this example, suppose we had an extra x sitting out in front of e to the x squared. Now that derivative of x squared, which has an x in it as a factor, has a place to go. And now the method of substitution makes this integral yield. So we get e to the u over 2x times x. The x's cancel. We substitute, we get the integral of e to the u with respect to u, and then substituting u equals x squared back into my final answer finishes this antiderivative. So substitution is worth a try in any case where you have an inside function, a composition of two functions to deal with, but it doesn't always work. It's not a magical solution for every integral that we'll be able to do, and that's part of why the first half of our course this semester is so interesting.